This is Lab 5, Magnetic Braking with Faraday by Griffin Price. Now to introduce this lab, the purpose of it is to look at how a falling magnet interacts with an aluminum foil tube with keeping Faraday's law in mind. The system and surroundings, the system being the falling magnet and the surrounding being literally everything else. And some overview of the results are that added holes in resistivity do affect the speed of the falling magnet, and the experimental and computational models were very similar, with the experimental being 1.879 seconds and the computational being 1.876 seconds. Some fundamental principles we're going to be using in this is the Biot-Savart law, Newton's second law, Faraday's law, and Ohm's law. Now for the experimental model, I found the north pole of the magnet using an app from my phone that we previously used in Lab 3. I then used the tube's length and dropped the magnet through the tube while recording it on video using my phone. I meant to say phone instead of video again. And I repeated this 4 more times and averaged the 5 total times of each video to get an average time of 1.876 seconds. Okay, and some data that I used that you'll see later in the computational model is the tube length, 0.28 meters, tube width, 0.022 meters, the inner radius of the tube being 0.016 meters, the outer radius being 0.038 meters, and the resistivity of the tube being 2.65 times 10 to the negative 8. The magnet of the mass of the magnet being 0.016 kilograms, and the magnet mu being 1.12 am squared. Now, for the computational model, here is where I just listed some initial conditions like the mass of the magnet, the mu, magnitude of the magnet, the length of the tube, width of the tube, inner radius, outer radius. And you can also see in the top right, you can see a mu naught over 4 pi, resistivity, and the gravitational constant are listed as well. Now for this is part of the computational model that helps us compute the magnetic field and the magnetic flux. And as you can see, I did that using mu naught over 4 pi over r cubed times 3 dot mu hat and r hat times r hat minus mu, Biot-Savart law. And then in the bottom here, we calculated the flux actually with d flux over dt, and we use the Faraday's law to help us do that as well. Now with this is the loop in our computation. So basically what this is doing is it's well, first it finds the force of gravity, and then it loops over and over in the tube, rings to make the tube, and it's finding the deflux of each ring, the current, and then it's helping us model it, which you'll see in a little bit, the actual model of the tube and the current in the tube. It's also helping us compute the B field at each ring, and as you look to the right here, it also helps us find magnetic force of each ring, and since there's 2 forces at play, magnetic and gravity, we add those together to get the net force, and then we can also find magnetic velocity and position using Newton's second law. And yeah, so these are the results of the computational model. As you can see, we have a graph there, the result being 1.879 seconds, and to the right you see the actual modeled tube. And some notes on this would be that the blue and red, those are currents, the blue being clockwise current and the red being counterclockwise current, and the magnetic field from induced current opposes a change in flux. And now some possible sources of error could be that the video timer on my phone isn't exactly accurate with the length of time, and that some objects nearby from doing the experiment could have had their own magnetic field, which could interfere with results, obviously. The computational model could be more accurate if we added more rings to model the tube better. And the graph shows that there are 2 forces at play which balance out for the majority of the experiment. Now some what if questions. What if the resistivity of the conductor were reduced as close as possible to zero? How would the strength of the dynamics of the falling magnet change? The strength of the induced current would be greater. This would lead to a stronger opposing force, increasing braking effect. And what if holes or slots were cut into the tube? How would this affect the rings currents in your model? Holes and slots would weaken the strength of the induced current. This would weaken opposing force, which would decrease braking effect, allowing the magnet to fall more freely. Thank you.